Let's talk about collision theory. So collision theory basically describes how a reaction happens at like a very small scale. So at a very small level. So for collision theory, you have three things. In order for a reaction to happen, particles have to hit each other. So in this case, I have this reaction where water is reacting with another water molecule to form hydronium and the hydroxide ion. This is something known as the auto-ionization of water, but I'll be making a separate video for that. So yeah, this is a very special reaction. It's actually reversible, but you know, I'm not going to be talking about it in this video. I'm not going to be diving too deep. But anyways, for this reaction to occur, well, these two water molecules have to hit each other in the first place, right, for this reaction to occur. The second thing is that the particles have to hit each other in the correct orientation. So notice how, in order for these two water molecules to react, one water molecule has to sort of be zooming towards the other water molecule and be sort of knocking off or attacking this hydrogen, right? This oxygen attacks this hydrogen and therefore sort of steals this hydrogen away from this other water molecule. That's why it becomes H3O plus, right? This water molecule right over here has stole a hydrogen or hydrogen ion or a proton. And in this case, it has gained one hydrogen atom, right? Hydrogen ion, sorry. Now, the water molecule has stole a hydrogen atom, right? It wants to steal the other hydrogen atom from the other water molecule. So if the water molecules start zooming at each other where the oxygen atoms are now facing each other, well then this is the improper orientation, right? The oxygen wants to react with this hydrogen. It doesn't want to react with this other oxygen. So this reaction will not occur if they just zoom at each other like this. And in addition, remember that oxygen in a water molecule, that's going to have a partial negative charge, right? And like charges repel each other. So in fact, the oxygens don't even want to be close to each other in the first place. Finally, the particles, they have to hit each other with enough energy. All right, it's sort of like an energy barrier. And that energy is called the activation energy. Think about when you're lighting up a match, right? If you have a match and you have like a matchbox, right? Now there's a reason why the match just does not light up on fire spontaneously, right? There's a reason why if you just take out a match from a matchbox, there's a reason why this match just does not catch on fire like instantaneously, right? You have to supply it with enough energy in order for it to catch on fire. That's why you have to scrape this match on this matchbox right over here to give it the initial boost of energy for this reaction to occur, right? You want to overcome this energy barrier, aka activation energy, for this reaction to occur. And we can represent that using a potential energy diagram. So a potential energy diagram looks something like this, where you have potential energy on the y-axis and a reaction progress on the x-axis. The farther you are on the x-axis, the more progress the reaction has made. Remember that this arrow right over here represents the potential energy for the reactants. I'm just going to put R here to represent reactants, right? Because this right over here, you're starting out as a reactant, then you have to overcome this activation energy barrier, right? You have to overcome an energy barrier, and then you turn into your products, right? Now, when you're starting off, the reactants have some potential energy. That's going to be, the potential energy of the reactants, and likewise, after you finish the reaction, this right over here, this distance right over here represents the potential energy for the products. This length right over here represents the activation energy for the forward reaction. What do I mean by that? Let's say if A turns into B and B turns back into A. So this is something known as a reversible reaction. It goes both ways. So A can turn into B, B can also turn back into A. Now, in order for A to turn into B, what has to happen is A has to overcome an initial barrier of energy, right? The activation energy for this reaction to happen. But notice how this reaction can go both ways, right? I said how B can also turn back into A. So if B wants to turn back into A, it has to actually overcome this barrier of energy right over here, right? It has to overcome this barrier of energy. And this barrier right over here is called the activation energy, except it's for the reverse reaction, right? It's for the reverse reaction. If A wants to turn into B, it has to overcome a barrier of energy. If B wants to turn back into A, it has to overcome its own barrier of energy that's separate from what A is experiencing, okay? Notice how starting from the potential energy of the reactants to the potential energy of the products, you have actually lost potential energy. And this value right over here, the difference, so basically the difference between the potential energy of the products and the potential energy of the reactants. I'm just going to put R for reactants. This is something known as your change in enthalpy, aka the heat of reaction. So delta H, change in enthalpy. This is also known as the heat of reaction. It's basically how much has your potential energy changed from the start to the end. In this case, we're losing potential energy, as you can see, right? Because the potential energy of the products is less than where it originally started. In this case, you have lost energy, and your delta H value, your change in enthalpy, will be negative, right? Because you've lost potential energy. This reaction is exothermic, meaning that you lost energy, right? Energy is being released. If we had a reaction that looks something like this, I'm not going to label the x and y axis because x-axis reaction progress, y-axis is potential energy. But if the reaction looks something like this, where notice how the potential energy of the products is greater than the potential energy of the reactants, notice how you have gained potential energy. So your delta H value, your change in enthalpy, also called the heat of the reaction, it will be positive. And therefore, you are absorbing heat. So this will be an endothermic process. Endothermic reaction. Endothermic. Now, collision theory, that's pretty cool, all right? But let's dive in a little bit deeper to collision theory. And for that, we will be taking a look at the Arrhenius equation. So some dude named Arrhenius, right, wanted to see the effects of temperature on the rate constant, okay? Now, if you do not know what the rate constant is, I will be making a video maybe sometime in a couple of days about, the orders for the reaction and the rate laws and all of that. So stay tuned for that. If you do not know what the rate constant is, I will highly suggest, watching a video on that first before coming back to this. Anyways, he saw that there was like a linear relationship between 1 over the temperature and the rate constant and ln of the rate constant. There was a linear relationship. Linear relationships can be modeled by y is equal to mx plus b. Y in this case is ln of k. M represents our slope, and the slope actually turns out to be the negative activation energy divided by R, which is the gas constant. X in this case is 1 over T, right? That's our X sort of value. I mean, if you just multiply these two things together, we can just condense this into RT, right? We can just condense it into that. And this is going to be plus B. B is our y-intercept. In this case, our y-intercept is ln of A. ln of A. Solving for K, we raise both sides to the E power. Cancels out. That cancels out, right? E and ln cancels out. You get K is equal to E to the negative activation energy divided by RT. Divided by RT. And this is going to be multiplied by E to the ln A due to exponent properties. E and ln cancels out, so you're just going to be left with A. And this is the Arrhenius equation. I will be talking about what each of these variables mean. K is, once again, this is our rate constant. This is something known as a rate constant. A is something known as the frequency factor. And let me just bring this collision theory down. R is a constant, right? So I'm not going to worry about that. T is our temperature. And remember, this is our activation energy. Activation energy. Now, what is the frequency factor, you might be asking? Well, frequency factor pretty much combines the first two things of collision theory into one thing. All right, the frequency factor just represents kind of the amount of collisions, basically the collision frequency, right? How often do the molecules bump into each other? And it represents the orientation probability. So how likely is it that, when two molecules collide, well, they collide with the correct orientation? So it combines these two factors into one variable, essentially. All right. Now, this part of the equation right over here represents kind of the third thing about collision theory. Particles have to hit each other with the correct, with enough energy, right? Because you notice how activation energy is in our equation. So we know that it has to be dealing with energy, right? Now, here are kind of some things that I want you to consider. What happens to the rate of the reaction? So this is something known as the rate constant. Rate constant. And the rate constant K is going to be proportional to the rate of the reaction. Rate of reaction. Don't worry, once again, if you do not know this, I'll be making a video on this. But just know that in this case, K is going to be proportional to the rate of the reaction. So if our K value is bigger, the rate is bigger. All right. Now, what happens if I increase the frequency factor? AKA, what happens when more particles collide with each other and more of them collide with the correct orientation? What happens to the rate of the reaction? Will it increase or will it decrease? Well, think about this logically, right? If you have more particles, more collisions, and more particle orientation that's correct, right? If more particles collide with each other that has the correct orientation, well, the rate of our reaction will increase. So increasing the frequency factor increases the rate of a reaction, and that makes logical sense, right? Because of what I just said. But yeah, more collisions and more kind of correct orientations means more successful sort of reactions going on, right? This also makes sense mathematically, because if you increase A from a mathematical perspective, you're also increasing K, assuming that you keep all of these values constant, right? If your activation energy is the same, if this is a constant, E is a constant, temperature, if we assume that's constant, right? If we held all of these variables constant, but we just increase the value of A, that's going to increase the rate constant from a mathematical perspective. And that increases the rate of the reaction, because remember that K is proportional to the rate of the reaction. So for increasing K, we increase the rate of the reaction. Okay, so let me just write this down. Increasing A increases the rate of the reaction. Now, what happens if we decrease the activation energy? What do you think will happen to the rate constant? AKA, if you decrease the activation energy, what do you think will happen to the rate of the reaction? Will it increase or will it decrease? Well, if you decrease the activation energy for a reaction, that means that more particles are going to be able to have the successful amount of energy in their collisions for the reaction to happen, right? If you decrease the activation energy, that means it's going to be easier for the particles to react with each other, because it takes less energy for the reaction to occur. So decreasing the activation energy increases the rate of the reaction. If you're dealing with negative exponents, right? If you have 2 to the negative first power, that's going to be much greater than 2 to the negative 1,000 power, right? So when you're dealing with negative exponents and this numerator right over here, the numerator is very big, that's going to lead to a small value. So in this case, if I decrease activation energy, what that's essentially doing is, because we have a negative exponent here, you're going to have e to a very small value, right? Similar to 2 to the negative first power, right? You're going to have e to a very small value. And that's going to be, and in turn, that's going to lead to a higher rate constant than if you were to do e to the very big value, right? Because if your activation energy is very big, that's going to make the numerator very big. And in turn, you're going to get a very, 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 very small value for this. And therefore, your rate constant is going to be very small. Therefore, the rate of the reaction will be smaller, because K is proportional to the rate of the reaction. And the opposite is true, right? If you decrease the activation energy, right, in return, that will give you a somewhat bigger value for this whole thing right over here. That means you'll have a bigger rate constant, meaning that you'll have a bigger rate of reaction. Finally, you have temperature. Now, what do you think will happen if you increase the temperature? Well, guess what? The rate of the reaction will increase, because if you increase the temperature, you're essentially increasing the amount of energy for the particles, right? The particles will now move at a faster speed, and therefore more particles will have the amount of energy required to overcome the activation energy, right? You'll find out that more particles are able to collide with enough energy for this reaction to happen. This also makes mathematical sense, because if you're increasing the denominator in this, that's going to make this value very small. And when you're dealing with negative exponents, then that's like a good thing in the context of our equation, because this value right over here will be pretty big, right? And then you'll have like a bigger rate constant. If the temperature was very small, well, then the numerator becomes very big, right? If you have a small denominator, that means the whole value right over here will be bigger. E to the negative of a very big value, that's going to lead to a very small value, small rate constant, small rate, right? So, you don't really have to memorize. You don't have to memorize the proof for this formula. You don't have to memorize sort of the mathematical relationships, but you should be able to logically sort of know what's going on, right? You don't have to know the exact mathematical relationships, but you do have to know that, increasing the frequency and, the amount of collisions, whatever, increases the rate of reaction, right? You have to understand this logically. There's also one last thing to know. Speaking of increasing the temperature, increasing the rate of the reaction, notice how I have something known as a Maxwell-Boltzmann distribution. Now, this should be familiar to y'all. I'm assuming that, because this is kinetics unit, and Unit 3, you encounter the Maxwell-Boltzmann distribution. So this should be kind of familiar to you. So let's say if we have a sample of our reactant at different temperatures, and let's say that this is the activation energy for our reaction. Notice how at a higher temperature, more particles have enough energy in order for the reaction to occur, right? More particles have enough energy, which is symbolized by the area under the curve. While if you have a very colder temperature, well, notice how less particles actually have enough energy for this reaction to occur. So this just, once again, supports the claim that higher temperature means higher rate of reaction. Feel free to pause the video for any of these practice problems. So let's say if we have two reactions with the same activation energy, reaction A has a frequency factor of 10 to the 10, reaction B has a frequency factor of 10 to the 13. Which reaction is faster, assuming the temperature is the same? Well, remember that the frequency factor pretty much represents the probability that particles collide with the correct orientation, and it's basically representing the total amount of collisions that happen. So because we have the same activation energy, and actually, if I write out the formula, it's going to be K is equal to the frequency factor times e to the negative activation energy divided by RT. Now remember how I said temperature and activation energy is constant, right? Same activation energy, same temperature. That means that this whole entire thing right over here is the same for both reactions. Only A is changing. If we increase A, we're increasing the amount of frequencies, and we're the frequency of collision, and we're increasing the probability that two particles collide with the correct orientation. So therefore, reaction B, because it has the bigger frequency factor, the rate will be faster. So the reaction will be faster for reaction B. Reaction is exothermic by 100 kilojoules per mole. The activation energy is this. Draw to describe the shape of the energy diagram and the activation energy for the reverse reaction. So we're going to draw out our potential energy diagram here. Reaction progress. Y-axis is potential energy. A reaction is exothermic, meaning that it releases energy. So that means that the potential energy for the products is going to be less than what you started with, right? Because you have released some of the energy. It says the reaction is exothermic by 100 kilojoules per mole. That means that we have lost 100 kilojoules of heat, pretty much. So, our delta H value, change in enthalpy, is equal to 100 kilojoules. And the activation energy for the forward reaction, so if we're trying to get from reactants to products, we're going to have to hit an activation energy of 150 kilojoules. So 150 kilojoules of energy in order for the activation energy for the forward reaction. Just put this here. All right, so the activation energy for the forward reaction, in order to get from reactants to products, have to overcome 150 kilojoules of energy, and our change in enthalpy is 100 kilojoules. So the shape of the energy diagram, well, it's going to be the shape where the reactants are going to be, the potential energy of reactants is going to be greater than the potential energy of the products. And also remember to have this little bump here. The activation energy for the reverse reaction, meaning that essentially just means that if we're trying to get from products back to reactants, well, what's the activation energy for that? How much energy do I have to overcome? Essentially, it's going to be this value right over here. Right? Because you have to, if you're in the product side, you have to overcome this barrier of energy in order for the reaction to occur. This barrier of energy, notice how it's equal to these two arrows added up together, right? The big arrow is equal to two little arrows added up together. The two little arrows have their own respective values. So essentially, what you do is you just add up the 150 kilojoules with the 100 kilojoules, right? And then you should get the activation energy for the reverse reaction, 250 kilojoules, right? Just add this activation energy right over here, and then the change in enthalpy, and then after that you should get this big arrow, activation energy for the reverse.